Hello to everyone. Thank you for giving me the opportunity to speak today. My work is a joint work with Professor Giovanni Vincenzi about a particular Diophantine equation that you can read in the title. Our presentation begins with a brief historical overview to contextualize the problem. We will then cover the required technical preliminaries. Following that, we will calculate a first bound on solutions and finally a second short bound. The work is inspired by previous works. The first one on the sum of two terms of Fibonacci numbers equal to a power of 2 by Bravo and Luca in 2016. Then, over the years, equations about the sum of 3, 4, and 5 numbers were solved. Then, the last year, Jeong and Park solved the problem for the sum of two squares of Fibonacci numbers equal to a power of 2. And so we extend the recent work to the case of three squares. Some preliminaries. First, we recall the Binet formula is a well-known formula, but just for notation, I recall here. In fact, we will use alpha for the golden ratio and beta for the other solution of a characteristical polynomial. Then we show a useful inequality in which Fn lies between two consecutive powers of golden ratio. Another important definition is the logarithmic height. In particular, started from the definition of eta, that is an algebraic number of degree d with a minimal polynomial in equation 3, where eta I are all solutions of this polynomial. The logarithmic height of eta is defined as in equation 4, where they appear leading coefficient, the degree of the polynomial, and possibly eta I. Moreover, H satisfies three properties we will use during the proof, these three properties. Okay, the most important theorem we will use is the Matveev's theorem, in which we have a number lambda as the product of powers of algebraic numbers, minus 1, in equation 5. So the theorem states that if lambda is different from 0, we have a lower bound on the log of lambda. And in this lower bound, they appear A1, A, T, and B that are defined here in these 2 points. But why we will use this theorem? Thanks to it, we can find an upper bound on variables n, m, and l of our equation. But this bound is too large. So to reduce it, we will use this lemma, that is Duell-Lapeto lemma, based on continued fraction. In this lemma, we have a positive integer m and an irrational number gamma, and we must search a convergent of continued fraction of gamma such that the denominator is greater than 6m. So we know from theory that we can write this number in an infinite continued fraction. So convergents are infinite and denominators are increasing. So in a point, we have a q greater than 6m. Moreover, the theorem states that defining epsilon in this way, if epsilon is greater than 0, so there aren't solutions for this inequality. So we will calculate with the math software a denominator such that is greater than 6m and epsilon is greater than 0. Okay, first, using the previous inequality and simple inequalities on Fibonacci numbers, we obtain a bound on A. So the first lemma we want to prove is this, in which we have the first bound on n, the large bound. Okay. Remember the Matthews theorem, and in particular, remember how to calculate B and AI. Okay. First, the proof is divided in 3 steps. Okay. We find the bound on n minus m, then n minus l, and finally n. So we write the equation with Binet formula, and isolating the dominant term, we obtain this bound from which, dividing by the dominant term, we obtain a restriction on the expression defined by lambda 1. And this lambda 1, remember the lambda in Matveev theorem. In fact, applying Matveev's theorem on lambda 1, we calculate B, where we use the bound on A, then A1, A2, and A3, and we get these 2 inequalities from which we obtain the bound on n minus m. Then we rewrite the equation, including also the second square here, and dividing by the first sum, we obtain a restriction on the expression defined by lambda 2. This is lambda 2. And so applying Matveev's theorem on lambda 2, we calculate B, A1, A2, A3, and A4, and get these 2 inequalities from which we obtain a bound on n minus L. And here we use the bound on n minus m. So the previous bound, the bound of step 1. Finally, we include the third square, and dividing by these 2 sums, we obtain a restriction on the expression defined by lambda 3. So applying Matveev's theorem for the third time, we obtain these 2 inequalities, and so a bound on n, depending on the bound on n minus m and n minus l. Okay, here n appears on left and right of the inequality, so using a math software, we calculate the bound on n. Okay, so the bound is too large, we will use the Duella-Pareto lemma, and the new bound is 259. We used math software, we used SageMath, and these are all solutions that we have calculated with software. Okay, so in essence, we have proved the following theorem. All non-trivial solutions to the Diophantine equation are these. Okay, now I can explain why we used the word unexpected in the title. If we compare this theorem with the theorem on solutions of equation with 2 squares, we have that solutions are the same. In fact, in our solution, we have always L equal to 0. So a new addend doesn't contribute. And this is why we use the unexpected. So now I will briefly explain the proof of the reduction because of time, but who wants slides are available for you. So in the first step, we use the bound on n and calculate a new bound on E and define this M. This is the M of the Duella-Pareto lemma. So using then inequalities on Fibonacci numbers, on Binet formula, sorry. So this is the Binet formula, we use the Binet formula, and we obtain this inequality, and applying logarithm on left and right, we define Z1 as the log of the right side of inequality, and using a symbol inequality here, Z1 is less than e to the power of Z1 minus 1, but this is lambda 1, and we know that is bounded by this expression. So dividing all for log alpha, we obtain this sequence of inequalities that that is an expression like in Duella-Pareto lemma. In fact, we use the same letters to define the various species, and we calculate Q with the math software, epsilon, and finally, as I said before, we obtain the bound on n minus m. Okay, now we do the same for the second step, observing that now n minus m assume numbers from 0 to 247. So the bound we obtain is the biggest one that contains all bounds for every value of n minus m. Because we, for every value, calculate the bound, because Q depend on this number, epsilon depend on this number, and then we obtain different bounds. This is the biggest one that contains all. And we do the same for the third step. Here we use combinations of values of n minus m and n minus l and obtain the bound on n. Okay, these are references. Thank you for your attention.